What do we really know about uranium? It's one of the heaviest naturally occurring metals on Earth. In terms of energy, a single uranium fuel pellet can contain about as much usable energy as a full ton of oil. That's why uranium has been used as nuclear fuel for decades. Because of uranium, nuclear energy became possible, and today, hundreds of nuclear reactors around the world are producing electricity right now. In this video, I'll explain how uranium is mined and the full journey from extraction all the way to ending up inside a nuclear reactor. Stay with me to the end, because this will change how you think about one of the most dangerous metals on Earth. For a lot of people, uranium sounds like one word: radiation. But it's not that simple. To understand what uranium really is, you need a few key facts. Natural uranium oxide has been known since ancient times. People used it in glazes for ceramics, coating dishes to make them more water-resistant, and also for decoration. In nature, uranium isn't found as pure metal. It's present as part of uranium ore. Uranium as a metal was first discovered by a German chemist at the end of the 18th century, and it was named after the planet Uranus, which had recently been discovered. For a long time, nobody suspected it had radioactive properties. People treated it like just another ordinary material. Then in 1840, a chemist in France proved that what people were dealing with wasn't pure metal at all, but uranium oxide. A year later, that same scientist isolated uranium in pure form, and it was thanks to uranium that, in 1896, Henry Becquerel accidentally discovered rays that were later called radioactivity. Uranium is a radioactive element, but how strong is its radioactivity? The longest living isotope is uranium-238. Its half-life is about 4.5 billion years. And because its half-life is so long, you could say it emits pretty weakly. Its alpha particles don't pass through human skin. There's even a story about Soviet academician Kurchatov. After working with uranium, he would simply wipe his hands with a cloth, and he did not suffer from radiation sickness. So if we're talking strictly about radioactivity, uranium itself is relatively weak. But then you might ask, how does a weakly radioactive metal become the main fuel for nuclear power plants? To understand that, you need the final and most important discovery: the process of uranium nuclear fission, which was discovered right before World War II. After that discovery, uranium mining ramped up all over the world. The idea is simple. If you hit the nucleus of uranium-235 with a neutron, it captures the neutron and starts to split. And that splitting process releases a truly enormous amount of energy. That discovery became the starting point for using uranium in nuclear power, and also for military purposes. More than 99% of uranium in nature is uranium-238, which is practically not dangerous to humans. But the isotope that matters most is uranium-235, and there's less than 1% of it in nature. Only this isotope can sustain a chain nuclear reaction, which is why it's used as fuel in nuclear reactors. And when it comes to military-grade uranium, in some places it hasn't really been produced at scale for decades because huge stockpiles were built long ago. Today, most uranium mining is aimed at producing fuel for nuclear power plants. Uranium mining gets even more interesting when you look at how much is actually out there. There isn't barely any uranium on Earth. There's quite a lot. It occurs more often than silver. The real problem is that large, rich deposits are rare. So in many cases, uranium has to be mined from deep underground shafts, sometimes up to about 0.6 miles deep, around 3,300 feet, or even deeper. Some of the largest reserves are found in Canada, Russia, Kazakhstan, and Australia. But the quality of deposits varies a lot. For example, in Russia, from 1 ton of ore you get, on average, about 1.5 kilograms of uranium, about 3.3 pounds. In other countries, the ratio can be different. A lot of people have heard scary stories about uranium mines, but very few even picture how normal metals are mined, let alone uranium. During the early Cold War era, there were legends that uranium mines were worked by criminals who were atoning for their guilt. There were also rumors that uranium miners had to wear lead underwear. Of course, that's exaggerated, but there's a grain of truth behind why these stories existed. Before World War II, the Soviet Union wasn't especially focused on uranium mining. But once it became clear the nuclear weapons race was accelerating, in 1943, Soviet geologists were given a task: find uranium deposits as quickly as possible and set up conditions to study them. At first, during the search for uranium ore, there was a severe shortage of equipment and technical tools. Miners faced danger every day from cave-ins and flooding, and they were exposed to high radiation doses. Later, they began using dosimeters to measure radiation levels. In mines about 0.6 miles deep, the temperature could get extremely high, up to 122 degrees Fahrenheit. Often, the biggest danger wasn't radiation itself, but dust containing particles of uranium and other heavy metals. If those enter the body, they can lead to serious disease. Radioactive radon gas in the air was also dangerous, but with proper ventilation, its concentration could be kept minimal. Today, of course, things are very different. Uranium deposits are searched for using aerial gamma surveys. Then exploration drilling is done, the rock is studied, reserves are estimated, and a mining and processing technology is selected. There are three main methods of mining uranium ore. First, open pit mining. This is used when uranium ore is close to the surface. With open pit mining, they dig a huge pit using heavy equipment. Excavators load the ore into dump trucks, which haul it to a processing facility. Second, underground mining. This is used when uranium ore lies deeper. With underground mining, a vertical shaft is drilled. The depth can reach about 1.2 miles, around 6,600 feet. Miners extract the ore and lift it to the surface in special elevators, then it's taken to a processing facility. This method strongly resembles ordinary coal mining. Third, in situ leaching, also called underground leaching. This method is fundamentally different from the first two. In the center of the hexagon, another well is drilled, and through it, a solution saturated with uranium salts is pumped to the surface. However, this is not uranium yet, only its oxide. Getting pure uranium is a long chain of chemical reactions and transformations. But even isolating the pure metal isn't enough. By itself, uranium in that form isn't very useful. To generate power in nuclear plants, it must be enriched. Natural uranium is a mixture of three isotopes: uranium-238, uranium-235, and uranium-234. And as we've already understood, only uranium-235 is suitable for nuclear energy. But unfortunately, its natural concentration is too low for stable operation in most modern nuclear reactors. Although, as far as I know, the RBMK reactor was designed so it can start on fuel made from natural uranium. But stability and safety of operation on such fuel are not guaranteed. So for nuclear power, uranium has to be enriched, meaning the concentration of uranium-235 must be increased. And uranium-238 is basically just a heavy gray metal. You could make an artillery shell out of it, or even a keychain. And that brings us to the key question. How do you separate uranium-238 from uranium-235? At the very beginning of the nuclear race, both in the US and in the Soviet Union, people explored diffusion separation, basically pushing uranium through something like a sieve. The idea was that the lighter 235 would slip through more easily, while the heavier 238 would lag behind. And manufacturing a sieve with incredibly tiny holes wasn't the hardest industrial problem in 1946. They started building huge enrichment facilities, and not just plants, but entire towns around them. And these diffusion plants consumed so much electricity that separate power stations had to be built nearby. Now imagine about 2,000 massive installations just to get around 100 grams of uranium-235. Today there are many enrichment methods and we won't go through all of them. I'll just say that modern enrichment is most often done with gas centrifuges. A centrifuge is conceptually simple. It's like a washing machine on spin cycle. Only here, gas is fed inside along with molecules containing uranium. Due to centrifugal force, the gas separates into heavier and lighter fractions. That mixture goes into the next centrifuge, and then the next, until the concentration of uranium-235 reaches the required level. Once the uranium-235 concentration is high enough, it's pressed into special pellets using lubricants that are later removed during high-temperature firing in furnaces. At the same time, in another workshop, special tubes are prepared for the fuel elements. At this stage, fuel assemblies are created using uranium-235 pellets, and those assemblies are then installed into the nuclear reactor. This is what the RBMK reactor lid looks like. Under it, standing vertically, there are fuel assemblies. One square is one assembly. If it's not too hard, write in the comments how many assemblies this reactor contains. And that's how uranium becomes part of the electricity-making process. But the story doesn't end there. Everything would be fine if the pellets didn't break down into other elements during the nuclear reaction. When that happens, reactor power weakens, and the chain reaction eventually slows and stops on its own. It can only be restarted after replacing the uranium in the active zone. Everything that has accumulated inside the tubes has to be unloaded from the reactor, and then either stored long-term or reprocessed for reuse. Uranium that has worked in a nuclear reactor is called irradiated, or burned, and the fuel assemblies are called spent nuclear fuel. Different countries handle this in different ways. Countries like Sweden, spent nuclear fuel is managed under strict safety rules, often stored securely for the long term, and in some cases sent for reprocessing as part of advanced fuel cycle work. In some countries, work is being carried out on a closed fuel cycle. This process makes it possible to reuse part of the spent nuclear fuel by creating new fuel assemblies for nuclear reactors. Logically, with this approach, there will be much less waste left. Why spend money storing nuclear waste if you can make part of it work again in a reactor? For this, there are special institutions that deal with reprocessing technologies, separating radioactive sludge into useful elements. Using manipulators, operators control equipment in hot cells. From high radiation, the operator is separated only by lead glass about a meter thick, about 3.3 feet. Just think about it. The cost of this glass can be around $1.3 million. Under radiation, the glass gradually loses its transparency and needs replacement. And all of this just to extract valuable material from nuclear waste that can be used to create new fuel assemblies. So that same uranium that was once mined deep underground, enriched to the required concentration, and then removed from the reactor as waste, goes back through furnaces and becomes a uranium pellet again. By the way, does the name polonium-210 mean anything to you? This chemical element is considered an ideal poison. It is more toxic than cyanide by 250,000 times. Polonium-210 can be extracted from uranium. Today, polonium is produced only at nuclear reactors and is used for different purposes, for example, making batteries for spacecraft. Worldwide, about 100 grams of polonium are produced per year. Just think, the price of 1 gram of polonium is equal to $4 million. With prices like that for chemicals, you'd expect the producer to be unbelievably wealthy, but in reality, it doesn't work that way. According to scientists' forecasts, around 2030, all large uranium deposits will be completely depleted. After that, development of hard-to-reach layers will begin, and prices will rise. What happens next is a big question. Even today, there's an intense struggle for control over uranium mines and deposits. This issue is strategic. Whoever controls uranium sources has enormous influence over the global nuclear energy industry, and can also affect the nuclear weapons market. I think we've figured out the story of uranium's discovery and how uranium takes part in nuclear energy.